Welcome back to the deep dive. Today we're doing something a little different. We are undertaking a very unique mission. We're
Oh,
diving into a single academic paper that is genuinely operating on, well, on two separate frequencies.
that's a great way to put it.
One is this world of, elegant, pure algebraic geometry, and the other is a radical, almost shocking meta commentary on the current state of artificial intelligence in research.
That's right. The paper is titled Extremal Descendant Integrals on Moduli Spaces of Curves, an inequality discovered and proved in collaboration with AI.
Wow.
And you, the listener, are probably immediately struck by that last part, right? The collaboration detail.
Absolutely.
So our goal is to unpack the math, and we will. It's about finding the maximum and minimum values of a specific, very complex interval, but maybe more importantly, to analyze the story of how this discovery and proof actually happened.
Because the human wasn't the one who found the simplest path.
Exactly, the AI was. This document, it fundamentally challenges what we even think of as mathematical authorship.
So we're going to treat it less like a textbook and more like a historical record, a record of a key turning point in human machine research.
A contract almost.
A contract, I like that. We're moving section by section, sentence by sentence, ensuring we rigorously understand the geometric context and the ethical implications of this groundbreaking partnership.
All right, let's get into it.
Let's start with the abstract itself, which immediately establishes the optimization problem. The author states, for the pure class intersection, numbers Langle-Calandelig on the moduli space of stable curves, we determine for which choices of ER1, ERN1, ER1, ER1 day H, the value of DEI becomes extremal.
Okay, a lot to unpack in that one sentence.
A lot.
We need to set the geometric scene first because this is where all the action happens. We are dealing with something called MGR1 sub G comma N, which is the moduli space of stable curves.
That sounds incredible abstract. What does the notation Mangle Talent Fred sub G comma N actually represent?
Think of it as a huge abstract collection of all possible geometric shapes. It's a kind of library,
Okay, a library.
and the indices tell you what's on the shelf. The index $G is the genus, which is just the number of holes, so a sphere is genus 0, a donut is genus 1, and so on.
Right.
The index dollars is the number of marked points, which are just a lot of distinct fixed spots on that curve.
So memD sub G comma N is the space that organizes or catalogs all curves with a specific number of holes G and a specific number of spots N.
Exactly. And they have to be stable, which is a technical condition that just ensures the space itself is well behaved.
Yeah.
It prevents curves that collapse or degenerate too easily. It keeps the library tidy.
Okay, so the domain is set. That's our library of shapes. Now, what are these Halley class intersection numbers, this D dollar?
No tau inclined tau at E equals the angle brackets containing tau sub E1 through tau sub En, close angle brackets, sub G. These are the core objects of a field called enumerative geometry.
Which is all about counting things, right?
It's all about counting things. The Chinese classes themselves, these are mathematical objects tied directly to those null mark points. They kind of capture the infinitesimal information about the curve shape right at that specific spot.
Okay.
And the intersection number, this DE, is what you get when you multiply a set of these geometric classes together and integrate them over the entire space, over the entire library, niln sub G, comma N.
Why do they call it an intersection number? Does something actually intersect?
In many geometric settings, yes, it literally counts the number of times different geometric conditions intersect each other. So the result is a rational number that tells you something about the geometry. The exponents, the AE sub I, they determine how strong the geometric constraint is at each of those marked points.
So the problem is actually pretty simple to state then.
Deceptively simple.
How do you distribute these exponent constraints, this vector, E1, E equals E1 through En, to get the biggest count or the smallest count?
That's the whole game.
All right, I think that covers the foundational geometry of that first sentence. Have we missed any nuances in setting up this optimization problem?
No, I think we've thoroughly unpacked it. We have a space of shapes and a way to get a number from those shapes by imposing conditions at marked points. The question is how to tune those conditions. Let's proceed to the result itself.
The abstract continues. The intersection number is minimal for powers of a single dollar class, i.e. all E dollars but one vanish, whereas maximal values are obtained for balanced vectors, vel by 1, for all dollar.
And this is immediately intuitive, isn't it?
It really is. The minimum occurs when the exponents are concentrated. All the mathematical weight is just jammed onto a single marked point, and the others are 0.
And the maximum.
The maximum occurs when the exponents are balanced, meaning they differ by at most 1. They're spread out as evenly as possible.
Exactly. This confirms a sort of universal combinatorial intuition. You see it everywhere. Symmetry and balance tend to maximize the complexity or value of an operation, whereas concentration minimizes it. This is the conjecture the AI confirmed.
Okay, so we've identified the minimum, which is the concentrated form, and the maximum, the balanced form. Shall we move to the method?
Let's do it, because this is where it gets interesting.
That brings us to the methodology paragraph, which reveals the surprising simplicity of the proof strategy. The proof uses the nefness of the Tyche classes combined with Khovansky-Teissier log concavity.
And this is the strategic shortcut the AI found. We need to briefly break down two terms here. First, nefness.
Nefness.
A class is nef, which stands for numerically effective if, when you intersect it with any curve in the space, the resulting number is non-negative. It's a key geometric property that signals a kind of positivity across the entire space.
And why does that positivity matter for an optimization problem?
Because nefness is the key that unlocks the door to the Khovansky-Teissier log concavity theorem. You can think of log concavity as the algebraic property that forces a sequence of numbers to be unimodal. Meaning it must increase to a single peak and then decrease. A classic bell curve shape, basically. So by applying this very general theorem to the intersection numbers, the AI realized that the sequence of values, as you shift weight from one exponent to another, must peak exactly at the balanced central point.
So that's the entire proof strategy.
That's the whole thing. A general property, nefness, allows the use of a general theorem, log concavity, which forces the maximum to be at the balance point.
That immediately establishes the tension of this paper, then. This is a complex, high-stakes problem. You mentioned it's linked to the monumental Witten-Kontsevich theorem, and it was solved by an AI using a simple general geometric property that human mathematicians had simply overlooked.
Or just didn't think to apply in this context. Precisely.
All right, we've covered the required technical foundation, nefness and log concavity. Have we sufficiently explained why these tools are applicable here?
I think so. The key is that nefness provides the positivity needed for the log concavity inequality to hold. Now we can move into the author's note, where the meta-narrative really begins.
The origin story is fantastic, the author writes. The question of finding extremal values of the Telsey intersection numbers first occurred to the author when looking for a toy problem to explore using the software OpenEvolve. The conjecture that balanced exponents lead to the maximal values is a natural guess, and was indeed discovered quickly by the tested model.
This is such a crucial detail. This wasn't a grand research project. The author was simply trying to find a toy problem to test an open-source evolutionary search system.
Just kicking the tires on some software.
Exactly. They chose a domain they knew, algebraic geometry, and the AI instantly produced the correct conjecture. The AI confirmed the natural guess quickly, but that guess had remained unproven.
So that covers the origin of the conjecture itself. Let's proceed to its novelty.
Right, because this is what's so remarkable, the author says. To the author's knowledge, this optimization-style problem was novel and not covered by existing literature. It is a simple and natural question, but somewhat orthogonal to the questions usually studied in enumerative geometry.
Orthogonal, that's the word.
It's the AI's strategic genius at work, if you want to call it that. Human mathematicians in this field were focused on these huge structural problems, finding complex generating functions or analyzing asymptotic behavior as the curves became infinitely complicated.
The big picture stuff.
The big picture. They completely skipped this simple optimization question in a finite fixed parameter space because it was orthogonal to the established research agenda. It just wasn't what people were looking at.
So AI, by lacking any human academic bias, acted as a cleaner, maybe, identifying elegant, low-hanging fruit.
I think that's a perfect way to put it.
We've established the novelty and positioning of the problem. What happened next?
The author sought validation. The note continues. After some experimental verification and presenting the conjecture to several colleagues who confirmed its open status, it was submitted as a problem to the Improof Bench project. This project collects research-level mathematics questions and tests them against a range of AI models. As part of this evaluation, the conjecture was independently proven by several such models without human intervention.
And there it is. That's the headline. The AI didn't just stumble upon the conjecture. It was formally submitted to a benchmark and was proven by multiple AI models without any human intervention.
It's a huge step. This moves AI from just being a research tool, like a calculator, to being an autonomous mathematical agent.
The problem went from conjecture to theorem, thanks to AI. What about the proof itself?
Well, this is the most fascinating part, the quality of the resulting proof. The proof itself turns out to be unexpectedly simple, bypassing the rich structural results on descendant invariance on inter n, and instead using just a few basic properties of C-classes, nefness and symmetry, together with general results on intersection numbers.
The AI found the most elegant, most generalizable route possible.
Yes. It didn't bother with the heavy machinery like the Witten-Koncevich theorem. It saw the core structure, that this was just a problem about intersecting nef classes, and applied the simple log concavity inequality. It prioritized simplicity over specialized complexity.
We've analyzed the elegance of the proof strategy. Now, the context for publication.
This leads directly to the author's remarkably candid assessment of the theorem's intrinsic value. It's really honest.
It is, the author says. As such, while the obtained theorem is a neat little result and original contribution to the literature, it would arguably be on the borderline of notability for a mathematical publication. We still opted to use this opportunity and write the present note to document the process that went into its discovery and subsequent write-up.
This completely shifts the paper's value. The mathematical result itself is, in the author's own words, borderline, but the methodology and documentation are revolutionary.
So the primary contribution of the paper isn't the theorem. It's the ethical transparency and the detailed accounting of the collaboration.
Which is why the author immediately proposes best practices. Apart from showcasing the current level of sophistication of AI, we also propose some best practices for attribution of AI use in mathematical writing. E.g., by marking human-generated text with a blue bar or underlines, whereas AI-generated text is marked in brown.
That visual formatting, convention blue for human, brown for AI, is a critical ethical solution to the agency problem, right? It makes transparency mandatory. You know exactly who or what wrote each sentence.
Absolutely. And finally, the author introduces the rigorous formalized approach. After an initial draft, we also added an alternative version of the proof, partially verified and lean. The argument is split into a purely combinatorial optimization theorem, formalized by Claude Code and GPT 5.2 with minimal guidance, and a geometric proposition.
Okay, so just to be clear, this means we have two proofs in this one paper.
That's right.
The first one, in Section 2, is the elegant, simple proof found by the AI. The second one, in Section 3, is a formalized, machine-verified proof, where the AI actually wrote the combinatorial core in this theorem prover language called lean.
And the human's job was just to provide the geometric input to link that formalized core to reality. This is where we see the human role morphing from primary writer to research director and validator.
That concludes the author's opening remarks, covering discovery, proof, and methodological contribution. We are now ready for the mathematical introduction.
The stage is set. Let's move to the formal mathematical introduction.
The introduction starts by formally defining the domain. It's written by the AI, marked in brown. Let $, with 2 descendant with 2 G's plus n dollars. The moduli space, millidollars of genus G with non-remarked points, has dimension dollars is 3G3 plus n dollars.
Okay, so that inequality, 2G asserts 2 plus n dollars G minus 2 plus n greater than 0, that's the stability condition we mentioned. It just keeps the geometry from becoming degenerate.
And the dimension, $EVs plus n dollars equals 3G minus 3 plus n, that's the crucial figure, right?
It's the total geometric capacity of the space. As we'll see, every integral we calculate must have exponents that sum up exactly to this number d, otherwise the integral just vanishes. It's 0.
We've confirmed the stability and dimension of the domain. Proceeding.
The next paragraph formally defines the tele classes.
For each marked point dollar, the cotangent line bundle, a dollar at that marking defines the telechi class C1, any H2 MGM.
Let's do a quick deep dive here. The cotangent line bundle, Lolar sub I, you can think of it as a collection of all the little tangent directions right at that specific marked point I. It captures local information about the curve's structure.
And the C1.
The C0 lie C1 of L sub I is the first Chern class. It's the standard way in geometry to translate a geometric object, like a bundle, into something you can calculate with. A cohomology class, it turns the geometry into a number or something close to it.
And it lives in the space Che2 on Nachi n Q RS2 of Mg, n Q.
Right, the second cohomology group of the moduli space with rational coefficients. That's just its formal algebraic home. The main point is that the teleclass C1 LXI sub I equals C1 of L sub I is the fundamental geometric building block for all these integrals.
We have rigorously defined the teleclasses. Moving to the integrals.
Next paragraph, also AI.
The descendant integrals, or intersection numbers of Taishan classes, Langle, Tau, and Wrangle are rational numbers that vanish unless sum I n a day.
So there's the full definition. The descendant integral, let's read it out, is Langle, Tau, and Wrangling. palen the angle brackets tau sub E1, tool angle brackets sub G, defined as the integral over mg comma n of pi1, 1 to the power E1, psin to the power En.
And it confirms the dimension constraint we just talked about.
Yes, the integral vanishes unless sum nei equals 1 to n of E sub I equals d. Intersection theory dictates that the total degree of the classes you're intersecting must equal the dimension of the space you're in. Otherwise, you get nothing.
We've confirmed the dimension constraint, now the significance of these numbers.
Right. Why do people care about these numbers so much?
Why?
The AI written text brings us to the high-stakes physics connection.
These integrals play a central role in the Witten-Kontsevich theorem, which establishes that their generating function is a tall function for the KdV hierarchy.
Okay, let's zoom out here for a mandatory deep dive. The Witten-Kontsevich theorem is, it's a monumental achievement of late 20th century mathematics.
What's the core idea?
It creates this unbelievable bridge between two completely different worlds. On one side, you have this very abstract algebraic geometry counting geometric objects on Mendenhall G, comma n, using these descendant integrals. On the other side, you have mathematical physics.
Specifically,
the Korteweg-de Vries equation, or KdV hierarchy.
Yeah.
This is a famous set of equations that governs things like nonlinear wave evolution, solitons.
and this theorem connects them.
It proves they are, in a deep sense, the same structure. It says if you take all these intersection numbers, dE lies, and package them into one giant formal power series, a generating function, that function is a tau function.
And the call function is?
A tau function is a very special kind of master solution to an integrable hierarchy, like KdV. It means these geometric counts, these DO values, are not random. They obey the incredibly rigid and precise laws of an integrable system from physics.
That establishes the context of the KdV hierarchy, so it really highlights the paradox here. The specific problem the AI solved might be borderline, but the numbers themselves are absolutely central to modern physics and geometry.
Exactly. Let's define the input space EDA.
The paper continues. Given $2 and EJ, 3D3 plus n be the set of valid exponent vectors.
So that's the formal definition of the domain for our optimization problem. The set, e.g., in G, n, is the set of all vectors E, which are E1 through En, in Z greater than or equal to 0 to the power n, such that the sum from J equals 1 to n of E sub J equals 3G minus 3 plus n.
It's a finite set.
Crucially, yes. Since CDAs is finite, a maximum and a minimum value for our function must exist. It's guaranteed.
We have the formal domain. Let's define the key structural property, balance.
Next is definition 1.1.
Definition 1.1. A vector abolian EGA n is balanced if each EJ localer for all $1 AJ and NS.
The definition of balanced is that the magnitude of E sub I minus E sub J is less than or equal to 1 for all I and J.
In other words, the entries are as equal as possible.
As equal as integers can be, yes. The next sentence explains this constructively. It says, you can write the dimension dGn plus bGd equals A times n plus b using Euclidean division.
Like when you learned long division in school.
Exactly. A is the quotient, b is the remainder. And the balanced vectors are just all the permutations of a vector that has b entries equal to a plus 1 and the rest and b of them equal to a. They're all clustered tightly around the average value, d dollars.
We have completed definition 1.1 and its constructive explanation. We now arrive at the main result.
Theorem 1.2.
Theorem 1.2, extremal descendants.
Yeah.
Let GL and Zn and 1 to the a with 2 graphs is 2 plus n dollars.
Just reiterating the constraints on g and n, it has to be a stable curve.
Part A is the minimum. A, minimum, the function dollar achieves its minimum at the concentrated vector 3g3 plus n, $0, $0, $100, or any permutation thereof, with value.
So the integral is angle tau g3 plus n rack tau angle brackets tau sub 3g minus 3 plus n times tau sub 0 to the power n minus 1 close angle bracket sub g.
And the value is frac 1 24gg1 divided by 24 to the power g times g factorial.
This is the minimum value. It occurs when all the geometric constraint d is concentrated on one point, represented by tau 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 sub d, and the others are the fundamental class tau tau sub 0. This formula itself is classical, known for decades.
We have the claim for the minimum. What about the maximum?
Part B confirms the AI's conjecture.
B maximum. The function dollar achieves its maximum on a balanced vector $3 and 1 bef2.
And that's the central claim. This is the new piece of knowledge discovered by the AI. It confirms the intuition that spreading the exponents out as evenly as possible maximizes the value of the integral.
Theorem 1.2 is complete. Let's discuss the historical context for these results.
Right, the next paragraph, which is a human AI split, does exactly that. It explains that the minimum value, part A, is well known.
It even follows from a known generating function identity, which is 1 plus the sum over g greater than or equal to 1 of t to the power g times the integral over mg comma 1 of ctsy 1 to the power 3d minus 2 equals the exponential of t over 24.
Right, that's equation 2. The new part is part B. The paper points out that for genus 0, when g equals 0, the result is actually easy to prove.
Why is that?
Because in genus 0, the integrals simplify to a simple closed formula. The integral in genus 0 is n minus 3 factorial divided by the product of e 1 factorial en factorial.
A multinomial coefficient.
Exactly. And it's a standard combinatorial result that a multinomial coefficient is maximized precisely when the denominators, the e factorials, are as equal as possible. The difficulty is in higher genus, where no such simple closed formula exists. That's the critical gap the AI proof strategy fills.
We've placed the theorem in context. We now look at the first two remarks.
Remark 1.3 just notes that the result was verified computationally for small cases.
Using SageMath and a package called abcycles, so they checked it for small g and n.
Right, it's supporting evidence before the formal proof. And remark 1.4, written by the human, clarifies that the maximum value is unique, but the vector achieving it isn't because of symmetry. You can permute the exponents and get the same value.
Okay, that brings us to question 1.5, which is the so what question, the direction for future research.
Yes, the human author poses a follow-up. Now that we know where the maximum occurs on a balanced vector, can we find a simple formula for its value?
The question is, for 3g3 plus n equals n plus b, does there exist a simple description, closed formula, generating function, recursion, all dots, for the balanced descendant invariant?
Which is, the maximum is the angle brackets containing tau sub a to the power n minus b times tau sub a plus 1 to the power b, close angle bracket sub g. Can we write down a nice formula for that number?
It's a great question for future human or AI research.
And the author suggests a place to start looking might be a simple case involving something called the dilaton equation.
Okay, mandatory deep dive 5. The dilaton equation. What is it?
The dilaton equation is another one of the fundamental structural relations from the Witten-Concevic framework. It's a recursive identity.
What does it do?
Its main function is to relate an integral that has a tau and tau sub 1 insertion to integrals that don't. It effectively lets you reduce the complexity of an integral or relate integrals with different numbers of marked points.
And the author suggests that in a certain regime where n is large compared to g, this equation allows a simplification.
Exactly. It lets you reduce the balanced invariant to a simpler known quantity. The equation is the angle brackets containing tau sub n minus the quantity 3, g minus 3 to the power 1, times tau sub 2 to the power 3, g minus 3, close angle bracket sub g equals the quantity 2, g minus 3 plus n factorial divided by the quantity 5, g minus 6 factorial times the angle brackets containing tau sub 2 to the power 3, g minus 3, close angle bracket sub g.
We have covered question 1.5 and the suggested simple regime. We are almost through the introduction.
The final paragraphs just reiterate the main points. The AI written part notes that this kind of optimization problem is somewhat unusual and suggests applying the same kind of thinking to other families of intersection numbers, like Hodge integrals or Hurwitz numbers.
And the human written outline just confirms the structure. Section 2 is the AI proof. Section 3 is the formalized proof.
Then there's a quick acknowledgement section, which is interesting. It thanks some people, but also notes the author was supported by SwissMapP and that the Improof Bench project received funding from Google DeepMind. So you see the institutional backing for this kind of AI research.
We have completed the introduction, definitions, theorem 1.2, and acknowledgements. We now proceed to the first proof section.
Let's do it. Part 2, the AI-generated proof.
Section 2 presents the first proof, starting with the maximum claim. The AI text begins. We write duaj dim mgn equals 3g3 plus dim throughout 2.1 maximal descendants. The following proof was generated by OpenAI's GPT-5 model. It is reproduced with only minimal formatting changes.
So confirmation of the source.
Yeah.
The elegance of this proof lies in its simplicity. It uses that log concavity principle we discussed.
The strategy is to fix everything except two exponents, ej sub I and the eje sub j.
Right. You define the background context, let's call it M, which is the product over k not equal to I and j of psi sub k to the power e sub k. That part is fixed. And you let qg is ei plus ejq equals e sub I plus e sub j. That's the dynamic part.
Then you define the slice sequence.
Yes, see now here. The sequence of sub t is the integral over mg comma n of ci sub I to the power t times ci sub j to the power q minus t times m. This sequence just varies the distribution of the total exponent sum q between the 2 points, from q all the way to q-all.
And step 1 of the proof is to establish 2 key properties of this sequence.
First, symmetry. Because all marked points are geometrically interchangeable, the sequence locant set sub t must be palindromic.
Meaning so q s q t s sub t equals s sub q minus t. The value for an exponent pair of, say, 3, 1 has to be the same as 1, 3 if their sum q is 4.
Exactly. And second, and this is the critical part, since the sub t classes are nef, the Khovansky-Teissier inequalities force the sequence sub t to be log concave.
The inequality is sec t1 st plus 1 sub t squared is greater than or equal to s sub t minus 1 times s sub t plus 1.
We fully defined the slice sequence sub t tis and its palindromicity, and we've stated its log concavity. Next, the consequence of this structure.
Log concavity plus palindromicity is the magical combination.
It really is. And this brings us to a mandatory deep dive on the unimodality of log concave palindromic sequences.
Let's walk through it. What does this combination guarantee?
It guarantees that the sequence must be unimodal. It increases to a single peak and then it decreases. To see why, you look at the ratios of consecutive terms. Let's call them twirry t, setr sub t equals s sub t plus 1 divided by s sub t.
Okay.
Log concavity, the sub t22 inequality, is equivalent to saying that these ratios are weakly decreasing. So a dirty quantity beak RTR sub t minus 1 is greater than or equal to r sub t. The sequence grows slower and slower, or decreases faster and faster.
And how does palindromicity come in?
Palindromicity, sat t, st, dot t, gives you a symmetry on the ratios. It forces the ratio to end of the sequence to be the reciprocal of the ratio at the beginning. You get war q1t, r sub q minus 1 minus t equals 1 over r sub t.
I see. So if the ratio at the start is, say, 2, the ratio at the end must be 12.
Exactly. Now you combine these two facts. The ratios are decreasing and they are symmetric via reciprocals. The only way this can work is if the ratios start at a value greater than or equal to 1, decrease towards 1 as they approach the middle, and they become less than or equal to 1 after the middle.
So say t plus 1 is bigger than stable before the midpoint and smaller after.
Precisely. The sequence increases strictly up to the center $2 and then strictly decreases away from it. The peak must occur exactly when the exponents are as close to equal as possible.
Unimodality is proven. This is the mechanism for balancing.
It's the whole engine of the proof. The AI summary says it best. In words, along the 2-point slice, the values increase up to the middle and then decrease.
So this means if a vector is unbalanced, if we have $E and $T such that $E$JJ plus 2, 2, then we are necessarily on the decreasing slope of that unimodal curve.
You have to be. Your larger exponent dollars is past the middle point $2 too. So if you take 1 unit from that larger entry and give it to the smaller entry, EJ, you're moving the exponent pair closer to the center, closer to the peak.
And the value of the integral must increase.
You must weakly increase. This gives us the key mechanism. Imbalance implies the value is not maximal.
The balancing step is complete. How does this prove the theorem?
Through iteration. You start with any vector E. If it's not balanced, you find 2 entries that differ by at least 2, and you apply the balancing step. The value of DE goes up or stays the same.
And you just repeat this process.
You repeat it. Because the total number of possible vectors is finite, and each step moves you closer to the balanced state, the process has to terminate. It terminates at a state where no 2 entries differ by more than 1, which is the definition of a balanced vector.
And since the value never decreased along the way, the maximum must be achieved at that balanced configuration.
That's the entire proof of the maximum, as generated by GPT-5. It's strikingly clean. The final line is just a little square symbol, QED, error.
But the proof requires that deep geometric justification, which the AI itself didn't necessarily provide. The paper includes remark 2.1 to justify the use of log concavity.
Right, and this is where we need our deep dive on the geometric foundations. We need to acknowledge the complexity of the space Bemg j to g, n. It's not a simple smooth manifold, it's a Deligne-Mumford stack, which is a highly singular generalized variety. It has orbifold points.
And classical theorems like Khovansky-Teissier don't always apply to these more complicated objects.
Generally, they require a smooth projective variety, or a scheme. So the human mathematician has to step in here to validate the AI's use of the tool.
And how do they do that?
The standard technique is to use a finite level structure cover. You find a related space, let's call it $6, that is a nice smooth projective variety, and which covers the singular space BenDC in a finite to one way.
So you do your work on the nice space.
You prove the inequality on the smooth space $6, where the theorems are known to hold. Then you use a result called the projection formula to push that result back down to the original moduli space. Because inequalities like this are preserved when you pull back geometric classes and integrate. The result holds rigorously on MGP.
So the human provides the geometric scaffolding necessary to hold up the AI's elegant but abstract argument.
That's a perfect summary. Remark 2.1. Justifying the log concavity tool is fully unpacked. Let's move to the minimum.
This proof was generated by Gemini 3 Pro. The strategy is essentially the reverse process.
Exactly. The AI states the plan. Show that iteratively concentrating exponents on a single marking yields a non-increasing sequence.
So you start with an unbalanced vector. You find the largest entry, say ETE sub k, and some other non-zero entry DE sub j.
Right, and you consider their sum Keulers equals EK plus E key. Since E key is maximal, it must be greater than or equal to the midpoint $2. So you are already on the decreasing side of that unimodal slice sequence.
So moving the exponents further away from the balance center by taking all the weight from E and putting it on HEPA moves you further down the slope.
It pushes the distribution away from the peak, guaranteeing the value of decreases or at worst stays the same.
We've confirmed that concentration weakly decreases dPA dollars, now the final concentrated state.
You just iterate this concentration step. You keep sucking all the exponent weight onto your chosen maximal entry, E10. The process must terminate at the maximally concentrated vector, which is $2, D tail dollars, $0, which we call E and E sub min, and the value had to go down.
We've established the minimum is achieved at E, now calculating the value.
For this, the AI used the string equation, which requires our next deep dive.
The string equation, what is it?
Like the dilaton equation, it's another one of the core geometric relations from the Witten-Kontsevich theory. It's a recursive dimensional reduction tool.
Okay, what does it let you do?
Its function is to relate an integral that has a tau sub-zero insertion to a sum of integrals with one fewer marked point and reduced exponents. It's the mechanism for reducing the number of marked points in an integral.
And the integral here is Langle tau angle brackets tau sub d times tau sub 0 to the power n minus 1 close angle bracket sub g. It has n1 of these tau dollar insertions.
Right. The string equation is the angle brackets containing tau sub 0 times the product from I equals 1 to m of tau sub ai, close angle bracket sub g, equals the sum from j equals 1 to m of the angle brackets containing tau sub j minus 1, times the product over I not equal to j of tau sub ai, close angle bracket sub g.
That looks complicated. How does it simplify our integral?
It's actually very simple in our case. When we apply the equation to remove one of the total ones, the sum on the right-hand side only has one non-zero term. That's because the only non-zero exponent is d. All the other exponents are already 0, and you can't have tau 1 tau sub minus 1.
So every time we apply the string equation, the exponent d is reduced by 1, and 1 tau dollar insertion is removed.
Exactly. We repeat this none all the times. The reduction looks like this. The angle brackets containing tau sub 3g minus 3 plus n times tau sub 0 to the power n minus 1 equals the angle brackets containing tau sub 3g minus 4 plus n tau sub 0 to the power n minus 2, which equals ... The angle brackets containing tau sub 3g minus 2 close angle bracket sub g.
You end up with an integral over a space with just one marked point.
You end up with a single point integral tau angle brackets containing tau sub 3 g minus 2 close angle brackets sub g. And this value is a classical result.
The paper says its value is 124 GDG, 1 divided by 24 to the power g times g factorial.
Which is exactly the result claimed by the AI. It follows from the Witten-Kontsevich theorem, specifically from the partition function for one marked point. And that concludes the proof.
The proof of theorem 1.2a, generated by Gemini 3 Pro, is complete. We now transition to the alternative formalized approach in Section 3.
Let's do it. This section is all about modularity and abstraction.
The section setup, written by the AI, explains the goal. The key insight is to separate the abstract optimization argument from the geometric input. This modular structure clarifies the logical dependencies and yields a fully machine-verified proof of the combinatorial core.
So they're breaking the problem in two. Section 2 is a direct geometric argument. Section 3 first proves a completely abstract combinatorial principle and then separately verifies that the geometry fits that principle.
The AI formalized an abstract statement, theorem 3.1. It says, let's paraphrase, that any function dealer dollars on the space of integer compositions that satisfies three simple axioms must achieve its maximum at a balanced vector and its minimum at a concentrated one.
What are the three axioms?
Condition S is symmetry. The value can't depend on the order of the exponents. dE dollar of E composed with sigma equals d of E.
That makes sense for our geometric function.
Condition P is strict positivity, dE dollars. The intersection numbers are positive.
Also true.
And condition LC is log concavity. dE delta plus delta, dETL plus delta of E squared is greater than or equal to d of E minus delta I plus delta J times d of E plus delta I minus delta J. This is just the log concavity property, defined purely algebraically.
So this is the critical step. The AI is proving the abstract truth that symmetry plus log concavity plus positivity guarantees that balanced is maximal and concentrated is minimal.
Theorem 3.1, the abstract core proven in lean, is now understood. We must verify the geometric function dollar satisfies these axioms.
Right. The human's job is now reduced to proving proposition 3.2, showing that the actual geometric function, the descendant integral, satisfies those three axioms.
So the human proves the geometric link, and AI formalized the combinatorial deduction using lean. Let's quickly look at how the human proves the geometric properties align with the abstract axioms.
For symmetry, S, it's standard. They confirm that relabeling the marked points is an automorphism of the space that leaves the integral's value unchanged.
For positivity P, they just cite that it's a well-known result from the recursive formulas in the literature.
And for log concavity LC, the hardest one, the human proof again relies on referencing the general Khovansky-Teissier inequality. They use the same finite cover argument we discussed before to show that the geometric intersection product dE satisfies the required algebraic inequality.
Proposition 3.2 is complete, verifying all three axioms, S,
yeah.
L, C, P. The main theorem is thus proven via abstraction.
Exactly. Once the geometric inputs are verified by the human in proposition 3.2, the conclusion of the abstract AI formalized theorem 3.1 automatically applies, and you get the main result.
The modular structure just makes it so clear what the AI did versus what the human did.
Absolutely. The abstract core, the part relying purely on logic and combinatorics, was handled and machine verified by the AI. The human simply validated the boundary conditions. Does the real-world geometry meet the required logical inputs?
It's an incredible shift in workflow. Okay, we have completed the main mathematical content.
Let's switch gears to the appendices, where the full story of the methodology and ethics is told.
We shift now to Appendix A, the methodology, which tells the full research story. It begins by confirming the discovery happened during a hackathon centered on OpenEvolve. The initial goal was just to test the software on a toy problem.
The AI quickly found the conjecture, but the subsequent formal testing via the Improved Bench project yielded mixed results, which is important. It demonstrates the current limitations of AI in rigorous mathematics.
And this brings us to a crucial point that the paper explicitly calls out: AI hallucination in math.
This is a mandatory deep dive. It's a fascinating and slightly terrifying example.
The paper notes that one model, when trying to prove the conjecture, cited a reference that appears to be entirely made up.
Completely fabricated. The AI generated a non-existent paper, Y 2018, a proof of the concavity conjecture for intersection numbers of Brives the classes, Journal of Differential Geometry. It even included plausible volume and page numbers. It looked perfectly authoritative.
But it's a ghost.
It's a ghost. The human author traced the reference and confirmed that the journal volume it cited featured a totally different paper by a different author. The AI just hallucinated a source that would have perfectly proven its point.
This just underscores the absolute necessity of the human role, doesn't it? Even when an AI successfully generates a correct proof, it may simultaneously generate these highly sophisticated, undetectable fabrications.
The human has to remain the final arbiter of truth and bibliographic integrity. But the success was also undeniable. The appendix notes that multiple advanced models like GPT-5 and O3 converged on the correct log concavity proof strategy independently, so they found the right path, even if some of them also made up facts along the way.
Appendix A details are complete, tracing the entire research journey. We move to the proposed ethical standards.
Appendix B, best practices.
The author notes the ethical mandate to prevent AI hype. Because any AI-assisted result garners public attention, the author argues they have a duty to be transparent about its actual mathematical significance.
Which the author did right at the start by admitting the result was borderline in isolation. It's about responsible communication.
And the practical solutions proposed are simple but powerful. First, a detailed methodology section that includes prompts, tools, code, even the cost of the AI subscriptions used, $20 a month for ChatGPT Plus, for example.
Full transparency. And second, that mandatory visual separation of text. Blue for human, brown for AI.
This solves the agency problem. You know who or what wrote what. It makes the collaboration auditable and reproducible.
Appendix B is complete. We have finished the entire source document from title to the final email address.
So let's sum up. This paper really provides a crystal clear roadmap for the future of mathematical research.
I think so. On the mathematical side, the elegant insight is that sometimes the simplest path is overlooked. The AI found that the maximum value of these highly complex descendant integrals is achieved by a balanced distribution of exponents, and it proved it via the simple general principle of log concavity. It's a technique that's far less complicated than the established methods in that specific field.
And on the meta-narrative side, the core takeaway is the complete redefinition of the human role in research.
Without a doubt, AI can discover, prove, and formally verify sophisticated mathematical concepts independently. The human mathematician's irreplaceable value shifts to defining the problem space, bridging the abstract with the geometric reality, verifying against hallucinations, and most importantly, providing the ethical stewardship and transparency necessary to document this new era of collaboration.
So here's the final thought for you to mull over. If the AI continues to find these elegant, orthogonal solutions that human strategic focus had previously ignored, what new avenues of research are going to open up?
And maybe more profoundly, if the primary contribution of a future mathematical paper is its methodology section and its attribution protocol, how long until the human is simply the necessary editor, the validator, ensuring truth and coherence in a landscape that's increasingly dominated by machine-generated knowledge?
We'll leave you with those profound questions. Thank you for undertaking this deep dive into the future of research with us.
Welcome to the Deep Dive. Today, we are taking on, I think, our most ambitious project yet. We're going to be guided by a very strict, self-imposed set of rules we're calling the unabridged protocol.
That's right. The mission is a perfect and complete understanding of a single, highly technical paper.
And we're going to do that by analyzing it strictly line by line, sentence by sentence, no jumping ahead.
And we should say up front, we're committing to a really deep foundational discussion. The source is a paper titled Extremal Descendant Integrals on Moduli Spaces of Curves, an inequality discovered and proved in collaboration with AI.
What a title.
It's a fantastic collision of, on the one hand, pure algebraic geometry, really deep stuff in enumerative invariance, and on the other, the absolute cutting edge of AI in generating mathematical proofs.
So our goal isn't just to tell you the final result, the theorem. It's to understand the entire process, the internal logic, from discovery to verification.
Exactly. We're going to operate as if we have infinite time. The pace is going to be deliberately, almost painfully slow.
All right, let's start at the very beginning then. The title itself. Let's deconstruct every single word. Extremal descendant integrals on moduli spaces of curves. An inequality discovered and proved in collaboration with AI.
It's a perfect roadmap, really. The first part, extremal values. That tells you right away this is an optimization problem.
We're looking for a maximum and a minimum.
Precisely. We're hunting for the absolute highest and lowest possible values that some mathematical quantity can take.
And that quantity is the second part, descendant integrals. We mentioned these are pretty specialized.
They are. Think of them as very specific numbers you get from doing a kind of calculus on a geometric space. They're intersection numbers of things called psi classes, and they're controlled by a vector of numbers, an input vector E. The whole game is finding which E gives you the biggest or smallest answer.
Okay, part 3 on moduli spaces of curves. This is the geometric world where this all happens.
Right. This is the stage. The space MGN is this vast catalog of all possible stable algebraic curves. It's the domain we're integrating over.
And then the fourth part, the part that makes this paper so timely, collaboration with AI.
And that's not just a gimmick. It signals that the methodology, the how, is just as important as the mathematical what. It really changes the whole context.
Okay, let's do our first completeness check, as per the protocol. Completeness check 1. Have we fully established the core ideas from the title? The optimization theme, the mathematical objects, and the AI context?
I think so, yeah. The goal is clear. Find the vectors E that extremize this function, dE. Let's move to the abstract, the very first sentence.
All right, the abstract begins. For the pure psi class intersection numbers dE, equals the integral of tau sub e 1 through tau sub e n in genus G on the moduli space mgn of stable curves. We determine for which choices of e equals e1 through en, the value of d of e becomes extremal.
Wow. Okay, that one sentence is just incredibly dense. It's got all the notation packed right in. We have to, under the protocol, do a really extended digression here.
Let's start with the notation for the psi classes. They use this tau symbol, te.
Right, and it's important to separate the geometry from the notation. The actual geometric object is the psi class. And to be super granular, the psi class psi is what you get when you take the first Chern class, psi of something called the cotangent line bundle, lie, at the ith marked point on your curve.
So that C operation is what turns a geometric thing, this bundle, into an algebraic thing we can actually calculate with.
Exactly. It moves it into the world of cohomology. The notation, that's more of a tradition that comes from the field of integrable systems from the Witten-Kontsevich theorem. It's just a shorthand for the integral of C raised to some power.
Got it. Okay, now for the big one, the domain itself, the moduli space, MGN. Let's spend some real time here.
We have to. MGN is the space that, in a sense, contains all stable curves. So a curve has a genus, G, that's the number of holes, like a donut has genus 1. And it has n distinct marked points on it, like little labels, P, E, A, and so on.
And the word stability is key here, you said.
It is absolutely essential. A curve is stable if it has a finite number of automorphisms, which is a fancy way of saying it can't have too many self-symmetries. If it's too symmetric, it's unstable. This condition is what ensures that the moduli space itself, Mg, Mau n, is a nice, compact, well-behaved object that we can actually do our calculus on.
So it's the landscape for the whole problem. The function dE is defined over this space.
Yes. It takes in that vector of exponents, e, and it spits out a single rational number, the result of the integration over this entire moduli space. And we're trying to find which e makes that number as big or as small as possible.
Okay, completeness check 2. We have, I think, thoroughly unpacked that first sentence. We've covered the notation, the foundational geometric concepts, and the function dE. Shall we move on to the actual result, the minimum value?
Yes, I think that was a good, deep foundation. Let's proceed.
The abstract continues, describing the minimal case. The intersection number is minimal for powers of a single psi class, i.e. all I but one vanish.
So this is what they call the concentrated vector. If the total dimension we need to sum to is d, this vector looks like d, 0, 0, 0, 0.
Meaning you put all your eggs in one basket.
Exactly. You stack all of the complexity, all of the dimension of this intersection onto a single marked point. And that, counterintuitively or not, gives you the absolute smallest possible value.
Why would that be? What's the intuition there?
The deep reason, which we'll see in the proof, is this property of unimodality, or being mound-shaped. The value is maximized when things are balanced in the middle. So if you move as far away from the middle as you can to the absolute boundary of the configuration space, you get the minimum. This is the most extreme configuration possible.
Okay, that makes sense. Now for the main event, the maximal case, whereas maximal values are obtained for balanced vectors, where the absolute value of E minus EJ is less than or equal to 1 for all IJ.
And this is the big discovery, the new result that the AI systems found. A balanced vector is one where the exponents are spread out as evenly as possible.
Like if the total dimension D was, say, 10, and you had 3 points, a balanced vector would be something like 4, 3, 3.
Perfect example. The difference between any two components is at most 1. This feels very intuitive if you've ever tried to maximize, say, a product of numbers with a fixed sum. Spreading it out evenly is usually the way to go.
And the abstract immediately gives us the toolkit for proving this. The proof uses the nefness of the psi classes combined with Kavonsky-Teissier log concavity.
All right, another mandatory deep digression is required here. These are the two pillars of the proof. Let's start with nefness.
Nef, as in NEF, it's short for numerically effective. We said this means that if you take a psi class, π, and you intersect it with any curve living inside the moduli space, the result is a non-negative number.
Right. It's a kind of positivity condition. And you should think of it as the geometric entry ticket. It's the prerequisite property that the psi classes must have for the really powerful algebraic machinery to apply. If they weren't nef, the whole argument would collapse.
So nefness opens the door. And what's behind the door is this Kavonsky-Teissier log concavity. That sounds imposing.
It's a very deep result in algebraic geometry. It's a powerful generalization of older theorems. And what it does is it applies to intersection products of these Neff classes. The result it gives you is this algebraic property of log concavity.
And we define that as the inequality STO ST1 plus 1 for some sequence of number saint.
Exactly. And what that inequality guarantees mathematically is that the sequence of values is unimodal. It has to go up, hit a peak, and then go down. It can't have multiple bumps. And since we'll see that balancing the exponents means moving toward the center of the sequence, this log concavity is the engine that proves the balanced vectors give the maximum.
Completeness check 3.
Mhm.
Okay, that covers the entire abstract. We understand the question, the answer for the minimum and maximum, and the core geometric and algebraic tools, neffness and log concavity, that make the proof work.
Yep, the abstract did its job perfectly. Now, let's move on to the author's note, which is where the story gets really interesting. The focus shifts completely to the AI.
Right. The note starts, and this is marked as human-generated text. The whole question came up as a toy problem to explore using the software OpenEvolve. The conjecture itself, that balanced vectors maximize the value, was a natural guess and was discovered quickly by the tested model.
We should unpack OpenEvolve. It's an open source system based on ideas from DeepMind's AlphaVolve. It's designed to do evolutionary searches, it tries lots of things, sees what works, and evolves towards a solution. The key here is that the AI wasn't told what to look for. It was just given the function and told to optimize it, and it found this pattern very quickly.
And this next line is fascinating. The author says the problem was somewhat orthogonal to the questions usually studied in enumerative geometry.
That's a huge point. It suggests a kind of cognitive bias in the human research community. Everyone was focused on the intricate, beautiful machinery of generating functions and recursions from the Witten-Kontsevich theory. The AI, having no such biases, just asked the simplest, most direct question, what's the biggest value? And found an answer using much more general tools.
So after the discovery, they needed to verify it. The note says the conjecture was submitted to the Improof Bench project, and this is the key line, it was independently proven by several such models without human intervention.
The implication of that is just massive. This isn't just AI as a fancy calculator anymore. This is multiple distinct AI systems autonomously generating a correct, novel, research-level proof in pure mathematics. The fact that different models converged on the same proof strategy gives it enormous weight.
And the proof itself turned out to be, in the author's words, unexpectedly simple. It bypassed all that complex machinery we just mentioned and instead used just a few basic properties, neffness, symmetry, and these general results on intersection numbers.
That's the real beauty of it. The AI found the shortest logical path. It realized you don't need the specialized tools of this specific subfield. All you need are a couple of fundamental properties of the geometric space and one very powerful, very general inequality.
The author is also refreshingly honest, saying the result on its own might be on the borderline of notability.
Right, which shows the real value of the paper isn't just the theorem, it's the demonstration of the AI's capability. The how is more important than the what.
The note then shifts to this new meta-theme. Attribution, they marked human text with a blue bar and AI text with a brown bar.
This is so important. It's setting a new standard for academic honesty in this new era. You can see exactly what part of the intellectual work was done by the human and what was done by the machine. It solves the credit problem right at the source.
And finally, they mentioned an alternative proof in Section 3, which was formalized in Lean. And that formalization was done by Claude Code and GPT 5.2.
Okay, another mandatory digression. Lean. A formal proof assistant like Lean is a different beast entirely from a natural language proof. It's not about writing a convincing argument for a human. It's about translating a proof into a computer-checkable format, down to the absolute fundamental axioms of logic.
So it's machine verified to be 100% correct.
100% logically sound, yes. The computer checks every single step. So the AI didn't just write a proof. It helped generate a proof that is, in a sense, mathematically perfect and unassailable.
Completeness check 4. We've made it to the author's note. We have the discovery story, the independent AI verification, the two different proof approaches, one geometric, one formalized, and the new attribution standard. Shall we finally dive into Section 1, the introduction?
That was a fantastic setup. Let's proceed to the first block of AI-generated text.
The introduction begins, and the AI is setting the stage. Let Gn be non-negative integers with 2g minus 2 plus n greater than 0.
And we just reiterate, this is the stability condition. G is the genus, n is the number of marked points. This inequality, 2g2 plus n0, is the technical rule that ensures our moduli space, MGN, is well-behaved and not one of the few unstable cases, like a sphere with only 1 or 2 marked points.
Next, the dimension. The moduli space MGN has dimension d equals 3g minus 3 plus n.
And this dimension formula, d, is absolutely fundamental. Let's spend a moment on why it's 3g3 plus n. This number d literally counts the number of independent parameters or degrees of freedom you have when describing one of these curves. For a curve of genus G, it takes 3g3 complex numbers to specify its shape. Then you have n more degrees of freedom, one for the position of each of the n marked points.
And this number d is the magic number that the exponents in our vector e have to sum up to.
Yes. If the sum of the exponents doesn't equal the dimension of the space, the integral is automatically 0. It's the core constraint of the whole problem.
Okay, let's use our pronunciation protocol here.
Right. So the expression type is the dimension formula.
The latex is d equals 3, 2 plus n.
And the phonetic transcription is d is equal to 3g minus 3 plus n.
Then the AI restates the formal definition of the psi class. For each marked point I, the cotangent line bundle Li at that marking defines the psi class ECHI, which is in H, M, G, N, and Q.
Let's break down that last part. H, N, G, and Q. This is the home of these psi classes. H, N is the second cohomology group, which is where these kinds of geometric objects live once you've turned them into algebraic ones. And the Q just means we're working with rational numbers as our coefficients.
Okay, let's do the protocol for that one as well.
Sure. The expression type is the psi class definition.
Latex is DH, HNG,
Phonetic transcription, PA psi sub I is equal to C1 of L sub I, which is an element of H2 of M sub G, comma N, with coefficients in Q.
Completeness check 5. All right. That covers the basic setup from the AI, the constraints, the dimension, and the formal definition of the psi classes. Are we ready to move on to the integral itself?
Yes, the foundation is laid. Let's get to the main object of study.
The AI continues. The descendant integrals are defined as the integral over MGN of the product of psi to the Ia up to Ia to the Ia, and they are rational numbers that vanish unless the sum of the Ei equals D.
And let's do the protocol for that integral notation, the one with the angle brackets.
Right. The expression type is the definition of the descendant integral.
The latex is Satiq Yorseg, MGN. MGN.
And phonetically, you would say. The integral of tau sub E1 through tau sub En in genus G is defined as the integral over M sub G comma N of Ci sub 1 to the power E1 through Pi sub N to the power En.
And again, there's that crucial vanishing condition. The sum of the exponents must exactly match the dimension of the space.
Which leads us to the reason why anyone cares so deeply about these specific numbers. These integrals play a central role in the Witten-Kontsevich theorem, which establishes that their generating function is a tau function for the KdV hierarchy.
We have to do another extended digression here. This is the big connection. The Witten-Kontsevich theorem is this celebrated, profound link between the world of pure geometry counting curves and calculating these integrals and the world of mathematical physics, specifically a set of equations called the Korteweg-de Vries, or KdV hierarchy.
So these numbers, these dE values, are not just random. They are the coefficients of a giant, powerful function that solves these important physical equations.
That's it exactly. That's why they are so intensely studied.
Okay, that brings us to the formal definition of the set of all possible exponents, EEJ. The AI defines it as the set of all n-tuples of non-negative integers, E, such that their sum is equal to 3g minus 3 plus n.
And let's run the protocol on that definition.
Expression type is the definition of the valid exponent vector set.
Latex is EG, EA, 8, EA, what's 3g, plus n.
Phonetic transcription. E of g comma n is the set of all vectors E, says that E is an n-tuple of non-negative integers where the sum of the components of E is equal to 3g minus 3 plus n.
So this is our search space. It's a finite but potentially very large set of all the valid ways to partition the dimension D among the n-marked points.
Completeness check 6. That gets us through all the formal definitions. We have the function dE and its domain e.g. or I to an n. Now we can finally get to definition 1.1, the definition of balanced.
Yes, this is the key to the main result.
Definition 1.1, a vector E in EGRN is balanced if the absolute value of EI minus EJ is less than or equal to 1 for all ij.
A beautifully simple condition. It just means you can't have any two exponents that are far apart. They all have to be clustered together.
And then it gives the constructive version, which I think is easier to grasp. Equivalently, writing 3g minus 3 plus n equals a times n plus b via Euclidean division. The balanced vectors are precisely the permutations of the vector with n minus b copies of a and b copies of a plus 1.
And let's dig into that Euclidean division d, at least in n plus b. This is just long division. D is the total sum, n is the number of parts, a is the quotient, it's the baseline, average value, and b is the remainder, which tells you exactly how many of the exponents need to be bumped up by 1 to make the sum work out perfectly.
So it's a completely deterministic way to construct the vector that achieves maximum balance.
It is. It's the unique configuration up to reordering the components.
Completeness check 7. We have now clearly defined what a balanced vector is, both with the inequality and the constructive method. I think we are ready for the main theorem, Theorem 1.2.
Let's do it. This is the heart of the paper.
Theorem 1.2 starts with the setup. Let g be a non-negative integer and n be a positive integer, with 2g minus 2 plus n greater than 0.
And notice that small but important detail, n has to be a positive integer. This is the correction that the AI peer reviewer suggested, as we saw in the appendix. It avoids some trivial cases.
Okay, part A, the minimum case. A, minimum. The function d achieves its minimum at the concentrated vector, 3g minus 3 plus n, 0, 0, with value. And then there's the formula.
All right, let's apply the pronunciation protocol to that formula for the value.
The expression type is the integral value for the minimum.
The latex is a 3g3 plus n G1, 24gg.
And the phonetic transcription for that is the integral of tau sub 3g minus 3 plus n times tau sub 0 to the power n minus 1 in genus g is equal to 1 divided by the quantity 24 to the power g times g factorial.
And just look at the elegance of that result. The minimum value, 1, 24gg, only depends on the genus g. It's completely independent of how many marked points n you have. That's a deep and beautiful simplification.
Now for the new result, part B. B, maximum. The function d achieves its maximum on balanced vector e in EGN.
Simple, clear, and powerful. This is the core discovery that the AI made. The maximum value occurs when the complexity is spread as evenly as possible.
The paper then provides some context for these results, linking the minimum value to identity 2.
Yes, and we need to apply the protocol to this identity and then explain what it means. So the expression type is a generating function identity.
The latex is 1 plus EG1 PGT XPT 24.
And the phonetic transcription is 1 plus the summation over g greater than or equal to 1 of t to the power g times the integral over m sub g comma 1 of ps sub 1 to the power 3g minus 2 equals the exponential function of t divided by 24.
So what's the why here? Why is this relevant?
This is a famous result by Faber and Pantarapande. If you look at the power series expansion of xp224, the coefficient of the tg term is exactly 1, 24gg. This identity is what proves that the value of the one-point integral e.g. 2 sheg is that number, which, as we'll see, is what the concentrated integral reduces to.
Okay, and for the maximum case, it notes that for genus 0, the result is actually already known from the closed formula, identity 3.
Right, and let's run the protocol on that formula. It's the genus 0 closed formula.
The latex is S entry N3, EO CSE S3.
And phonetically, the integral of tau sub E1 through tau sub En in genus 0 equals the quantity n minus 3 factorial divided by the product of E1 factorial through En factorial.
And the connection here is just basic combinatorics, right?
It is. To maximize that fraction, you need to minimize the denominator, the product of the factorials. And for a fixed sum, the product E0 at EO is smallest when all the E are as close to equal as possible. In other words, when the vector E is balanced. So for GO0, the theorem is a known fact. The real challenge is proving it for GO1, where no such simple formula exists.
Completeness check 8. We've now covered the main theorem and the crucial context for both the minimum and maximum cases, including the special GO0 case. Let's move on to the remarks.
Yep, let's proceed to the follow-up commentary.
Remark 1.3 notes that the result was computationally checked for G and N up to 11 using a SageMath package.
Just good scientific practice. Before you try to prove something, run some experiments to see if it's actually true. This gives confidence in the conjecture.
Remark 1.4 points out that the maximum isn't necessarily unique. You have permutations and sometimes plateaus may occur.
Right. The proof will only show a weak inequality, that balancing never decreases the value. It doesn't guarantee it strictly increases it every time. And of course, if 433 is a maximizer, then so is 343.
This all leads to question 1.5, which they call the hard problem. We have a simple formula for the minimum value. So is there a simple formula for the maximum value?
This is the natural next step. We know which vector gives the maximum, but we don't have a nice way to calculate the value at that vector. They're asking for a formula for this balanced descendant integral. Let's apply the protocol to the expression.
The expression type is the balanced descendant invariant.
The latex is OANBA plus 1b.
And the phonetic transcription is the integral of tau sub a to the power n minus b times tau sub a plus 1 to the power b in genus G.
Calculating that number for general G is the new research frontier opened up by this paper.
They then explore one specific case where n is very large compared to G, and they use something called the dilaton equation to simplify the integral.
Yes, and we should just briefly say the dilaton equation is another one of these fundamental recursive relations, like the string equation we'll see later.
Yeah.
It helps you simplify integrals that have terse terms. In this special case, the balanced vector has lots of terms, so they can reduce the problem.
But it doesn't solve it completely. It just reduces it to another still difficult integral.
Exactly. It simplifies but doesn't solve.
The introduction then concludes with the AI outlook, where the AI itself suggests looking at similar extremal questions for other types of integrals, like Hodge integrals.
Which is just a fascinating glimpse into the future. The AI isn't just a prover, it's acting as a strategist, suggesting new research directions for its human collaborators.
Completeness check 9. That finishes the entire introduction. We've covered the setup, the theorem, the context, and the open questions.
Yeah.
We are now ready to dive into section 2, the AI-generated proof.
Let's do it. This is the raw output from GPT-5.
The preamble says the proof was generated by GPT-5 and is reproduced with only minimal formatting changes. It starts with the proof of Part B, the maximum case. Step 1 is two-point slice and its basic properties.
This is a classic strategy in optimization. If you have a problem with many variables, you freeze all but two of them and see how the function behaves as you vary just those two.
So they isolate two exponents, EI and EJ, and let their sum be a fixed number Q. Everything else is bundled into a term they call M.
Right, M is the part of the integral that doesn't change. Now they can define a sequence, saint, which only depends on one variable, t. This sequence tracks the value of the integral as they shift the q units of dimension between points I and j.
And let's use the protocol for that saint definition.
The expression type is the slice sequence definition.
Latex, AIM-GM, phonetic transcription. The sequence S sub t is defined as the integral over m sub g comma n of ci sub I to the power t times ti psi sub j to the power q minus t times the term m.
The first property they establish for this sequence is palindromicity, ST-SQT, and that comes directly from the symmetry of the space. Swapping the labels on points I and j doesn't change the geometry, so the integral must be the same. This means swapping t for qt gives the same value. The sequence is symmetric.
Completeness check 10. Okay, step 1 is done. They've reduced the problem to a one-dimensional symmetric sequence. Saint dear. Let's move to step 2, the geometric heart of the argument.
This is where the magic happens.
Step 2, Khovansky-Teissier log concavity. The proof states that because the psi classes are NEF, they can apply the Khovansky-Teissier inequalities.
And this gives them the crucial algebraic property. We need to run the protocol on the formal inequality they present.
Okay, the expression type is the Khovansky-Teissier inequality.
The latex is
ET1 BQT plus 1 BQT1. And the phonetic transcription is the square of the integral of a to the power t, b to the power q minus t, times the product h3 through hd is greater than or equal to the integral of a to the power t minus 1, b to the power q minus t plus 1, times the product h3 through hd multiplied by the integral of a to the power t plus 1, b to the power q minus t minus 1, times the product h3 through hd.
So by plugging in A, B, B, and the rest into M, this big geometric theorem translates directly into a simple algebraic statement about our sequence, SJU or FT1, ST plus 1, which is the definition of log concavity.
Completeness check 11. Step 2 is complete. The geometry is given as log concavity for a sequence sant. Now, in step 3, they analyze the consequences of that.
Exactly. Now it's just pure algebra.
Step 3, monotonicity towards the middle. They define a ratio, RT plus 1. Inequality. Log concavity means this ratio has to be weakly decreasing. Palindromicity means RQT1, 1 art.
And when you combine those two facts, a decreasing sequence and this reflection property, it forces the sequence to be unimodal.
The conclusion is stated. For TQ2, the ratio art must be greater than or equal to 1, which means st plus 1 O sin 2. The sequence increases up to the middle, and past the middle, it decreases.
This is the local optimization result. Along any two-point slice, the value is maximized when the two exponents are as close to equal as possible.
Completeness check 12. So we have unimodality. We know the sequence is mound-shaped. Let's see how they use this to build the global proof in step 4.
This is the iterative part of the argument.
Step 4, the balancing step. They say, suppose you have two exponents, a and a, that differ by at least 2, so a plus 2.
Then you are on the decreasing side of that mound-shaped curve. The larger exponent, AA, is past the halfway point Q2.
And so the proof concludes that D must be less than or equal to SA1, which is the value you get by moving 1 unit from A to EA.
It's a rigorous argument. Shifting 1 unit of dimension from the bigger pile to the smaller pile moves you 1 step closer to the center of the mound, so the value cannot decrease. It can only stay the same or go up.
Which brings us to step 5, the conclusion. Starting from any vector E, repeatedly apply the balancing step.
And since the set of possible vectors is finite, and each step weakly increases the value while strictly reducing some measure of unbalancedness, the process has to stop.
And it stops when no more balancing steps are possible, which is, by definition, at a balanced vector. So DE for some balanced E, the proof is complete.
A really elegant argument found entirely by the AI.
Completeness check 13. We have finished the GPT-5 proof for the maximum. Now let's quickly go through section 2.2, the proof for the minimum.
This part uses the exact same logic, just in reverse.
Right, it starts with the concentrating step. It says take the largest exponent, eq, and any other non-zero exponent, ej.
Since eq is the biggest, we know we're on the non-decreasing part of the curve relative to eq. So if we move mass away from the center toward the boundary, the value should go down.
So the proof says that moving the entire value of e over to eq will result in a value that is less than or equal to the original. D, ek, ej, is greater than or equal to d, ek plus ej, 0.
And you just repeat that process. You find the biggest pile and empty all the other piles into it one by one. Each step, the value goes down or stays the same. Eventually, you end up at the completely concentrated vector.
Completeness check 14. Okay, the inequality part is done. We know the concentrated vector gives the minimum value. Now they just need to calculate what that value is.
And for that, they use another classic tool, the string equation.
We need to calculate oshik. The string equation is given as ushe otaikik oshe ot1 oshe.
And let's take a moment on that.
Yeah.
The string equation is a recursive formula that tells you how to handle an integral with a 2 in it. It says inserting a 2 is like taking a sum over terms where you lower one of the other exponents by 1.
In our case, we have n1 copies of 2. Since most of the other exponents are already 0 and Yosh is 0, applying the equation is simple.
It is. Each time you apply it, 1 Hz disappears, and the exponent on the big term, d, gets reduced by 1.
So the integral CG3 plus NORAS becomes 3G4 plus NHRs and so on, all the way down until all the terms are gone.
And you're left with the simple one-point integral, CGG2. And the value of that is the known classical result, 1, 24 GG.
Completeness check 15. That completes all of section 2. We've seen the AI's geometric proof for the max and the corresponding proof for the min. Now we pivot to section 3, the completely different formalized proof.
Yes, the shift here is from geometric intuition to pure, abstract, machine-checked logic.
The preamble says this section separates the abstract optimization logic, theorem 3.1, from the geometric facts, proposition 3.2.
This is a beautiful way to structure a proof. Isolate the core combinatorial argument and prove it rigorously. Then separately show that your geometric problem fits the requirements of that argument.
They start with theorem 3.1, the lean verified optimization theorem. It says that for any function d that satisfies 3 simple axioms, S, symmetry, OC, law of concavity, and P, strict positivity, the result holds.
And this is the power of abstraction. It doesn't matter if d comes from geometry or probability or physics. If it has these 3 properties, then its maximum must be on a balanced vector and its minimum on a concentrated one.
Let's quickly state the axioms. S is symmetry under permutation, P is the DE is always positive, and LC is the log concavity condition. Let's do the protocol for that one.
The expression type is the log concavity axiom.
Latex, DE. First, DE plus D.
I made a transcription. D of E squared is greater than or equal to D of E minus delta sub I plus delta sub J multiplied by D of E plus delta sub I minus delta sub J.
So the theorem says S, LC, and P are sufficient. Now, proposition 3.2 is the bridge. It's the human-written proof that our specific descendant function dE actually satisfies these three axioms.
And this is where the geometry comes back in. First, symmetry S. This follows from the fact that you can just relabel the marked points on the curves, and the geometry, and thus the integral, is unchanged.
Log concavity, LC. This is the hard one. It again comes from the Khovansky-Tessier inequality, but they had to do a technical maneuver because MGN is a stack, not a scheme.
Right. They use what's called a finite flat cover. They find a nice space X that maps down onto MGN, prove the inequality up on X where the rules are simpler, and then carefully push the result back down to MGN. It's a standard but crucial technique.
And finally, positivity, P. This just follows from the fact that these integrals are known to count geometric objects, and you can't have a negative count.
So the bridge is built. The geometric function satisfies the axioms of the abstract theorem.
Completeness check 17. Proposition 3.2 is verified. Now we just need to quickly walk through the abstract proof of theorem 3.1 itself as it was structured for Lean.
Yes, this is just formalizing the same ideas we saw in the AI's proof.
Section 3.1 and 3.2 formalize the slice sequence and prove that any sequence satisfying the axioms must be unimodal. This is lemma 3.7, the algebraic heart of the argument.
It's the same logic. Log concavity plus palindromicity implies unimodality. But here, every single step of the derivation has been checked by the Lean proof assistant. It's absolute.
Then section 3.3 proves the balancing step, lemma 3.8. If you have an unbalanced vector, balancing it increases d. The proof of theorem 3.1a then just says to iterate this process.
And it proves the process must terminate by showing that the sum of the squares of the exponents, a measure of imbalance, strictly decreases at each step.
Section 3.4 does the same for the concentrating step, lemma 3.9. Concentrating the vector decreases d. The proof of theorem 3.1b iterates this, and it terminates because the maximum entry strictly increases.
And with that, the entire abstract theorem is proven from first principles.
Completeness check 18. We have now completed the full formalized proof. This verifies the main theorem with machine-checked rigor. We have to now proceed to the appendices on methodology.
Yes, let's dive into the fascinating story in Appendix A.
Appendix A Part 1. On the discovery. It started with OpenEvolve, which found the G0 formula, and then generalized the pattern that spreading the exponents seems to give larger values.
So the AI is doing what good human mathematicians do. Solve a simple case, find a pattern, and conjecture that the pattern holds more generally.
Then, in A Part 2, the submission to Improof Bench, this is where it gets messy. Some models gave false counterexamples. One of them hallucinated a completely fake reference.
Which is such an important warning. You cannot blindly trust the output. The human verification step is non-negotiable. Even as multiple other models correctly converged on the Khovansky-Tessier strategy, this risk of fabrication is always present.
Section 8.3 details the formalization in Lean. The author had no prior Lean experience and used Claude Code and ChatGPT 5.2 for all the coding. They state they did not edit a single line of .lean code.
That's just remarkable. The AI is acting as an expert programmer in a highly specialized language, translating high-level mathematical ideas into formal, machine-readable code, with the human acting only as a project manager.
And finally, 8.4 on paper preparation. The AI tools were used for drafting, finding references, and proofreading. And it provided crucial corrections, like the N0 restriction and the fix to the string equation argument for GOU0.
So the AI is acting as a collaborator at every stage: discoverer, prover, formalizer, and finally, as a very sophisticated peer reviewer.
Completeness check 19. Appendix A is complete. It's a full case study of human-AI research collaboration. Let's finish with the proposed best practices in Appendix B.
Yes, the new rules of the road.
Proposal 1. Every paper using these tools should have a dedicated methodology section detailing the prompts, software, and code for reproducibility.
Just like in the experimental sciences, it brings a new level of transparency.
Proposal 2. Use visual formatting, the blue and brown bars, to make it clear who wrote what.
It solves the attribution problem cleanly and elegantly.
And Proposal 3. Contextualize the results for non-experts and avoid overstating the importance just because AI was involved.
A call for scientific humility, which the author of this paper models perfectly.
Completeness check 20. We have reached the end of the document. We've gone from the title to the final email address, following the unabridged protocol every step of the way.
The deep dive is complete. The key takeaway for you, the learner, is really about the strategy. Yes, the result is that balanced vectors maximize the integral. But the insight is that this was proven by applying a powerful general geometric inequality that the AI systems were able to identify as the shortest path, bypassing all the specialized machinery that humans had built up around the problem.
So we saw a new mathematical result discovered, a proof generated, a combinatorial core formally verified, and the academic paper itself co-authored, all with AI.
And that leaves me with a final provocative thought for you to consider. This paper suggests that many unsolved problems might not need new, more complicated theories. They might just be waiting for a known, powerful general principle to be applied in the right way. If an AI can now systematically test all known general principles against open conjectures, what does that mean for the future of human mathematical intuition and creativity?
A fascinating question. And on that note, thank you for joining us on this extremely granular deep dive into the future of mathematical research.
Welcome back to the deep dive. Today we are opening a source document that is, well, it's less a traditional research paper and more of a roadmap to the future of pure mathematics.
It really is. We are diving into a paper documenting the full, unprecedented collaboration between a human mathematician, Johannes SCHMITT, and three leading AI models, GPT-5, Claude Code, and Gemini 3 Pro.
The topic itself, extremal descendant integrals, is pretty specialized algebraic geometry.
Oh, absolutely. It's about finding the maximum and minimum values of certain geometric numbers on what's called the moduli space of curves. But, the real story here is the method.
Exactly. We are exploring a complete, transparent workflow, what we're calling the unabridged protocol. We're going to track the genesis of the problem, the AI-generated proofs, and the subsequent human verification all the way to the final citations.
Our mission, then, is to deconstruct this entire life cycle. We're going to understand the geometric state where this optimization takes place, the combinatorial rules that govern the solution, and this profound new workflow that led to a novel, formally verified theorem.
So let's start right at the top with the title itself. The title is Extremal Descendant Integrals on Moduli Spaces of Curves, an inequality discovered and proved in collaboration with AI.
Okay, let's just pause there. That title, it tells the whole story immediately. You have three parts. First, extremal descendant integrals.
Right, that tells us the task. It's an optimization problem. Find the biggest and smallest.
Precisely. Second, on moduli spaces of curves. That's the domain. The complicated, abstract, geometric world where this all happens.
And the third part, which is the kicker, discovered and proved in collaboration with AI.
The methodology is front and center. This is not just a paper where a computer was used as, like, a calculator. The AI is credited with discovery and proof generation.
Oh, okay, that covers the title. Let's move to the very first sentence of the abstract, which defines the object we're actually optimizing.
It says, for the pure Clay-class intersection numbers, daily dollars on the moduli space Nellia stable curves, we determine for which choices of E, the value of daily becomes extremal.
Wow, okay, that one sentence is an absolute fire hose of specialized notation. We absolutely have to pause here for our first mandatory digression. What on earth are MGM integracies in these TOSI classes?
Right, let's break it down. Let's start with the space, which is denoted metalline. That's the moduli space of stable curves. You can think of it as a sort of geometric container. It's an abstract space that gathers together all possible algebraic curves of a certain complexity.
And the complexity is defined by the letters, the dollar, and the dollars.
Exactly. The dollar is the genus, which you could just think of as the number of handles on a surface. A sphere is genus 0, a donut is genus 1, and so on. The dollars is the number of distinct marked points on that curve.
Okay, so melangiane is the collection of all possible donut shapes with dollar holes and specific points marked on them.
In a sense, yes. And that stability condition mentioned in the outline, $2, 2 plus nataline, that's just a technical requirement. It basically makes sure the space is well behaved and doesn't have too many weird symmetries, so we can actually do math on it.
Got it. It's the minimum entry fee for the geometry to work. Now, what about those other symbols, the tar classes and the tars?
So the tars class, which is written as tarsi, is a specific object from a field called cohomology. Geometrically, you can think of it as being defined by the cotangent line bundle at the ith marked point. These are the fundamental building blocks.
And the notation in the integral, that's just shorthand.
It's just shorthand. It's the same as pi2 twice sub I to the power e sub I. So that whole expression for z, the one with the angle brackets, that represents taking a product of these Thales classes, the first one raised to the power a to r, the second to 2 dollars, and so on. And then integrating that whole product over the entire space.
And the result of that big, complicated integral is just a single number.
Just a single rational number.
Yeah.
But it's a number that encodes incredibly deep information about the geometry of all those curves. We're looking for the choices of exponents, the vector area, that make that number as big or as small as possible.
Okay, so I think we've unpacked that first sentence. The object, the space, the goal. Have we missed any nuances?
No, I think that's a thorough breakdown. The setup is clear. Let's proceed to the next sentence, which gives the answer.
Right, the result. The second sentence states, the intersection number is minimal for powers of a single tile class, i.e., all $e but one vanish. Whereas maximal values are obtained for balanced vectors, AG for all E.
And there it is. The core finding, stated so simply. The minimum value happens for what the paper calls a concentrated vector. You take all the mathematical weight, so to speak,
right,
and you pile it all onto one single marked point, leaving all the others with zero.
All the complexity is bundled in one spot.
Right. And the maximum is the exact opposite. It's achieved by a balanced vector where the exponents are as equal as possible. No two exponents can differ by more than one.
So maximum value comes from maximal distribution. It's very intuitive, actually. It feels like it should be true.
It does feel intuitive, but proving it is another matter entirely. And that's what the next sentence is about. It says, the proof uses the nefness of the Tyche classes combined with Khovansky-Tyssier log concavity.
This immediately tells us the AI found a deep structural argument, not just some brute force calculation. So this is our next mandatory digression. What are nefness and log concavity?
Okay, so nef classes, which stands for numerically effective, you can think of them as having a kind of geometric positivity. It's a technical property, but it's the absolute prerequisite for using a whole class of powerful geometric inequalities that come from classical Hodge theory.
So nefness is the key that unlocks the door to the proof.
Exactly. And behind that door is the engine of the proof, Khovansky-Tyssier log concavity.
Log concavity. What does that mean in this context?
It's a property of a sequence of numbers. Imagine you have a sequence of these intersection numbers. Let's call it say for now. Log concavity means that for any term such the sequence is square is greater than or equal to the product of its two neighbors, actually at the time sub this qua.
So CST1 ST plus 1 and 2. It can't have sharp, jagged peaks. The sequence has to be smooth in a way.
Exactly. It forces the sequence of values to be well-behaved. And that is absolutely crucial because a positive symmetric sequence that is also log concave is forced to be unimodal.
Unimodal meaning it has only one peak.
One peak. It has to go up, hit a maximum, and then come back down. And because we know the sequence is also symmetric, because you can swap the marked points, that single peak must be right in the middle, at the point of maximum balance.
Wow. So the AI found this incredible shortcut. It didn't need to calculate any specific values. It just needed to prove this general shape property.
That's the genius of it. It's a purely qualitative argument.
Okay, that covers the first paragraph of the abstract, establishing the object of study, and the two key extremal results linked by log concavity. Have we missed any nuances there?
I think we've thoroughly unpacked it. The abstract clearly sets the stage for the unique origin story in the author's note. Let's proceed to the next section.
Right. This brings us to what is, for me, the most unique part of the paper. The author's note, which is marked with a blue bar, indicating it's human-generated text. This tells the story of how the problem even came to be.
And the origin is fascinating. The problem didn't come from, some famous open question list. It arose when the author, JOHANNES SCHMITT, was just looking for a toy problem to test an evolutionary search software called OpenEvolve.
So the human chose the general domain, these moduli space integrals, and then looking for a simple optimization task, basically just asked the machine to find the maximum.
Right, and the text says, the conjecture that balanced exponents lead to the maximal values is a natural guess, and was indeed discovered quickly by the tested model.
The machine experimentally confirmed the human's hunch almost instantly. But the really critical insight came next when the author realized the problem itself was apparently new. He calls it somewhat orthogonal to the questions usually studied in enumerative geometry.
And that is a huge point. Enumerative geometry usually asks questions like, what's the formula for this number? Or how many curves satisfy this condition? This question, which configuration gives the biggest number, was a kind of blind spot.
A blind spot that an AI, programmed with a simple optimization goal, immediately honed in on.
That's it. So after confirming that conjecture seemed to be new, the author submitted it to the Improved Bench project, which is a benchmark specifically for AI-proof generation.
And here we get to the most staggering statement in the second paragraph of the author's note. It says, as part of this evaluation, the conjecture was independently proven by several such models without human intervention.
It's just incredible. The AI didn't just find the answer experimentally. Multiple different AI systems were able to devise the entire proof strategy, that whole log concavity and unimodality argument, completely on their own. They reasoned their way to the geometric shortcut.
The author notes the proof was unexpectedly simple because it bypassed all that heavy machinery we mentioned, like the Witten-Kontsevich theorem. And so the paper exists not just because the theorem is important, he calls it on the borderline of notability, but specifically to document this groundbreaking process.
This paper is about how mathematics is being done now. And to do that transparently, the author introduces this unique attribution protocol. All human-generated text is marked in blue, and all AI-generated text is marked in brown.
That level of transparency is really a new standard. Okay, that covers the origin of the conjecture and the role of OpenEvolve in quickly validating the natural guess for the maximum. Have we missed any nuances here?
No, I think that's the core of it. The AI's quick confirmation is key. Let's move to the most important part.
Right.
The AI's role in the proof.
So we've just covered that, but the author's note goes deeper into the formalization process in the third paragraph. After the AI found this elegant informal proof, the author added an alternative proof, one that was partially verified in a program called Lean.
Right. Lean is a proof assistant. It's a software environment that can check a mathematical proof line by line and guarantee its logical correctness.
And the modular approach they used is just brilliant. They split the argument into two distinct parts.
Yes, this is key. Part 1 is a purely combinatorial optimization theorem, which was formalized in Lean by Claude Code and GPT 5.2. Part 2 is a geometric proposition, which was entirely human-written.
So let me see if I have this right. The machine proved with absolute certainty an abstract statement. If any function has properties S, P, and LC, then its maximum must be at a balanced point.
Correct. The machine verified the abstract rules of the game.
And then the human's job was just to prove the second part. Our specific geometric function, the descendant integral, actually follows those rules.
Exactly. It's the perfect division of labor. The AI handles the complex, tedious, but purely logical combinatorial argument, and the human handles the nuanced geometric translation and justification. It's a new kind of synergy.
We have fully analyzed the initial context, including the unique modular structure of the geometric and combinatorial arguments. Let's transition to the introduction.
Confirmed. Time for the rigorous definitions.
Section 1, which is marked as AI text, begins by just reiterating the mathematical setup. It sets the parameters. Genus, $7 marked points, with the stability condition 2 gemons 2 plus n dollars.
And it states the dimension of the moduli space des of dollars. The dimension d of dollars is given by the formula d equals 3g3 plus nd equals 3g minus 3 plus n.
And that dimension dollar is crucial because of the next point. The paper redefines the descendant integrals as this object here. Let's look at the notation. It's delta lingua, so that's the integral notation. Then it states the degree condition. The integral is 0 unless the sum of all the exponents equals the dimension, dollars.
Okay, this calls for our next mandatory digression. Intersection theory and dimension. Why does that sum have to be exactly dollars? Well, it's a fundamental concept in this kind of geometry. When you integrate a differential form or a cohomology class over a space, the degree of the form has to match the dimension of the space for you to get a non-zero number.
So each sum-C class has a certain degree, and when you multiply them together, their degrees add up.
That's right. Each fifth CI is in the second cohomology group, so it has degree 2. But in this context, we think of it as contributing 1 unit to the total dimension count. So the sum of the exponents, sum villains, must exactly match the dimension of the space. If the sum is less than dollars, you're integrating over a subspace that's too small, and the answer is 0.
Got it. It's a dimensional constraint that defines our entire search space. We only care about the exponent vectors that actually add up correctly.
Exactly. And the paragraph finishes by putting these integrals in their grand context. It says, these integrals play a central role in the Witten-Kontsevich theorem, which establishes that their generating function is a tau function for the KdV hierarchy.
Okay, that's another big one. Mandatory digression time. Witten-Kontsevich and KdV.
This is one of the most profound discoveries in modern mathematical physics. It connects the geometry of the moduli space of curves, these abstract intersection numbers, to the physics of integrable systems.
Specifically, the KdV equation, the one that describes, like, shallow water waves.
The very same, the Korteweg-de Vries equation. The theorem says that if you bundle all these descendant integrals up into one giant generating function, that function is a solution to this physical equation. It's a deep, deep structural result.
It sounds incredibly powerful and also incredibly complicated.
It is. The Witten-Kontsevich theorem gives you all sorts of tools like recursive formulas to calculate any of these numbers. But the beauty of the AI's proof is that it didn't need any of that heavy artillery. It found a shortcut that bypassed all of it.
We've covered the dimension constraint, the definition of the integral, and its high-level link to the KdV hierarchy. What's the next logical step?
The precise definition of the optimization domain, the set AG, EGN.
Right. The paper gives the formal set definition. It says the set is EGN. Here's the latex. EGEE, EGNEG, NVAEG intersegs, Serio N. Some J1 in EJ ends EJ, AGN plus NE.
Okay, and let's give the phonetic vocalization for the TTS. That's the set E of G and N is the set of vectors E equals E1 through En in the set of n tuples of non-negative integers, such that the sum from J equals 1 to n of E sub J equals 3G minus 3 plus n.
So it's just a formal way of saying it's the set of all valid exponent vectors.
Precisely. And the function we want to optimize is $, which maps from the set EGN to the rational numbers.
Then we get definition 1.1, which formally defines a balanced vector. It's a vector Toller in our set where the difference between any two components is at most 1.
And it gives a really helpful equivalent description. If you're at the total dimension of dollars, a dollar are dollars plus b, and it's, division with remainder, then the balanced vector is just permutation of a vector that has dollar entries equal to a plus, the rest equal to n.
It's the most evenly distributed partition of the integer all into new dollars.
Exactly. We have fully established the input domain EGN$ and the geometric meaning of a balanced vector. Let's state the main result.
Confirmed. Proceeding to the main theorem, theorem 1.2, which is titled Extremal Descendants.
The premise is just that we're in the stable range for $. Then it has two parts. Part A is about the minimum.
It says the minimum is achieved at a concentrated vector, for example, the vector 3g3 plus n 0l Bayman $. And it gives the exact formula for this minimum value.
Let's read out that formula. The expression is dola tau g3 plus n plus 1. The vocalization for that would be the intersection number of tau to the power 3g minus 3 plus n times tau naught to the power n minus 1 in genus G is equal to 1 over 24 to the power g times g factorial.
And what's amazing about that formula is how simple it is. It only depends on the genus, $. The number of marked points now completely drops out.
As long as you're in the stable range, yeah.
Yeah.
Okay, and part B is the new result about the maximum. Part B simply states that the maximum value of the function daedra is achieved on a balanced vector roller from our set EG dry.
The paper then notes that the minimum result, part A, is actually classical. It follows from a known generating function identity.
Right. The formula for that is given as formula 2. In the paper, it states $1 plus NG1 TG2 XET $24. The minimum value is basically the first non-trivial term of that series.
And it also discusses the genus 0 case. For Chi-Draus, part B is apparently easy to prove.
It is, because for genus 0, there's a beautiful, simple, closed formula for the integral. It's given as formula 3.
Let's see it. The formula is Langle tau and Wrangle pseudo 0 n3, which is just a multinomial coefficient. And we know from basic combinatorics that to maximize a multinomial coefficient, you need to make the numbers in the denominator, the x factorials, as equal as possible. So for $, the result is trivial.
The real novelty is extending this principle to higher genus, where no such simple formula exists. Exactly. We've analyzed the main theorem and the classical foundations for the minimum and the genus 0 maximum. We're now transitioning into the remarks.
Verified. Let's note the computational backing.
Remark 1.3 states that the result was checked computationally for small values of DSA and 9s up to 11 in both cases, using a Sage math package called add cycles.
Standard practice. You have a theoretical proof, but it's good to have some numerical evidence to back it up.
Right. Then remark 1.4 discusses uniqueness. It clarifies that the maximum isn't necessarily unique. You can obviously permute the entries of a balanced vector and get the same value.
And there might be plateaus where other non-balanced vectors give the same maximal value. So it's achieved on a balanced vector, not only on a balanced vector.
A good clarification to make.
Then we get to question 1.5, which is marked as human text. This is the author asking the natural follow-up question.
Yes. Since the AI proved where the maximum is, the human asks, what is the value of the maximum? Can we find a simple description like a formula or a generating function for DMAX.
This really shows that human-AI collaboration loop. The machine answers one question, which immediately tees up the next, more refined question for the human mathematician.
And the paper suggests a place to start looking. A simple regime where you can use another classical tool called the dilaton equation to reduce the complexity.
They give an example of this reduction. They show that one of these balanced invariants, specifically this one, Langle-Town, 3G3, 1, How 2G3, can be simplified.
And the simplified form is, well, let's read it. The expression is Furche, 2G3 plus n, 5G6, Langle-T plus n.
Okay, phonetically that's the intersection number of tau to the power n minus parentheses 3g minus 3 times tau 2 to the power 3g minus 3 in genus G equals the fraction of 2 minus 3 plus n factorial over 5g minus 6 factorial times the intersection number of tau 2 to the power 3g minus 3 in genus G.
So it reduces a complicated knot-point problem to a simpler one. It's a promising direction for future work.
The introductory section then concludes with a paragraph of AI contextualization.
Right. The AI notes that extremizing these kinds of enumerative invariants is somewhat unusual and proposes asking similar extremal questions for other types of integrals, like Hodge integrals or doubled Hurwitz numbers.
The AI is already planning its next research project.
It seems so. That completes the introductory section, highlighting the novelty, the open problem, and the computational backing. Let's quickly review the paper's outline and acknowledgments.
We are ready to look at the structure for the proofs.
The outline paragraph is human-written. It lays out the structure. Section 2 is the raw AI proof from GPT-5 and Gemini. Section 3 is the formalized modular proof, and the appendices cover methodology and attribution.
The acknowledgments are also human-written. The author thanks the organizers of the hackathon where some of this work was done and his colleagues for confirming the problem's novelty.
And importantly, he acknowledges financial support for the Improof Bench project from Google and DeepMind.
Okay. The entire front matter is covered. We now jump into the AI's first proof in Section 2.
Confirmed. Proceeding to Section 2.
Section 2 is titled Proof of the Main Theorem, and it's attributed to GPT-5 and Gemini. It starts with a simple setup note. $IOs 3G3 plus $n throughout.
Then we get into Section 2.1, Maximal Descendants, which is the proof of the maximum attributed to GPT-5.
But first, a very important note from the human author. He points out that the original AI output had an error in the genus 0 formula, which he had to correct.
Yes, this is a critical detail. It's a reminder that even when the core logic is sound, the AI can still make mistakes on boundary cases or technical details. Human verification is still absolutely essential.
Okay, so let's look at the AI's proof strategy. Step 1 is about setting up what it calls a two-point slice.
This is a classic simplification technique. Instead of trying to optimize all exponents at once, you fix all of them except for two, say ES and EJJ. You fix their sum, let's call it $2, so EI plus EE day.
And then you just study how the value of the integral changes as you move power between just those 2 points.
Exactly. It defines a one-dimensional sequence of values, where Dorgan goes from $0 to $. And the first property of this sequence is obvious. It has to be symmetric. 0 must equals $.
Right, because the underlying geometry doesn't care if you label the points or to dollar in dollars or to dollars, it's palindromic.
That covers the reduction of the problem to a two-variable slice sequence and its immediate symmetry. Let's move to the geometric input.
The simplification is elegant. Proceeding to Tavansky-Teissier.
Step 2 is where the geometry comes in. The foundational fact is that each KCA class is Neff on the moduli space.
Which we said earlier means it has a kind of geometric positivity.
Right. And because they are Neff, we can apply the powerful Tavansky-Teissier inequalities. The AI correctly identifies that this inequality, when applied to our slice sequence, implies discrete log concavity.
So we get our key relation, ST-togel, ST-1 plus 1 for all the terms in the middle of the sequence.
We've confirmed the critical log concavity inequality derived from the geometric properties of Neff classes. Now for the consequence.
Confirmed. Log concavity dictates the sequence's shape.
Step 3 is called monotonicity towards the middle. This is the payoff. A sequence that is positive, palindromic, and log concave must be unimodal.
It has to increase up to its midpoint, 2 color taus, and then decrease after that.
Exactly. The AI deduces that the ratio of successive terms, Twendel series plus 1 seer, must be a weakly decreasing sequence. And since symmetry forces the ratio to be 1 at the midpoint, it must be greater than 1 before the middle and less than 1 after.
So the sequence goes up, peaks, and goes down. That brings us to step 4, the balancing step.
This is the core of the argument. Suppose our original vector was imbalanced. Say, Ardo's was at least 2 more than AJR's. This means AJR's must be past the midpoint, $2 too.
And since it's past the midpoint, it's in the part of the sequence that's decreasing.
Correct. So by the unimodality we just proved, the value at Zahler must be less than or equal to the value just before it.
Which means if we take 1 unit of power from the larger exponent AJL and give it to the smaller one, AJLer, the total value of the integral weakly increases.
That's the balancing step. You can always improve an unbalanced vector, or at least not make it worse, by making it more balanced.
And step 5 is the conclusion. You just repeat this balancing step over and over.
Since the value never decreases, and there are only a finite number of possible exponent vectors, the process has to stop. And it stops when you can't balance anymore.
Which is when you've reached a balanced vector. That concludes the proof for the maximum.
That concludes the GPT-5 proof of the maximum. The logic is sound, relying only on the unimodality derived from geometric inequalities. Now let's quickly detail the geometric context.
Excellent. Let's briefly cover remark 2.1 before the minimum.
Remark 2.1 just adds a bit of technical geometric detail. It clarifies that log concavity is a special case of the Khovansky-Tysier inequalities, which can be proven using the Hodge index theorem.
But it also notes that this is complicated by the fact that MBA is a stack, not a smooth projective variety.
Right. It's a technicality, but an important one. The rigorous proof requires a trick. You have to lift the whole problem up to a nice, smooth space, a finite cover, where the classical theorems apply, and then project the inequality back down. The human author is confirming that this maneuver, which the AI didn't mention, is valid.
Okay, now let's move on to the proof of the minimum in section 2.2, which is attributed to Gemini 3 Pro.
The goal here is to show that iteratively concentrating the exponents onto a single marking results in a non-increasing sequence. It's basically the reverse of the balancing argument.
The first paragraph is the concentrating step. It says, let's take the biggest exponent, ekadral. If the vector isn't fully concentrated, there must be some other non-zero exponent, say iche.
And we look at the same two-point slice sequence as before, with total sum colors is the iche plus icheo. Since iche is the maximal exponent, it's guaranteed to be at or past the midpoint, $2.
So it's already in the non-increasing part of the sequence.
Exactly. So if we shift all the weight from eager over to x, we're moving from the point sec all the way to the endpoint sec. Since we're in the decreasing part of the sequence, the value cannot increase. Eager alders get smaller or stays the same.
So you can just keep doing this, consolidating all the little exponents onto the biggest one, and the value will only ever go down.
And eventually you end up with the fully concentrated vector. This proves that the minimum is achieved at such a vector.
The concentrating step successfully proved the minimum is reached by a concentrated vector by reversing the unimodality argument. Let's calculate the specific value.
Confirmed. The calculation uses the classical string equation.
The second paragraph is the calculation of this minimum value. We need to calculate the value of the integral for the vector e netherlongs. That's the integral angle tall one. So we
have the main term with exponent dollars and then dollar terms with exponent 0. The coll dollar class is special, and there's a tool for dealing with it called the string equation.
What does the string equation do?
It's a recursive formula. It lets you remove one tail dollar insertion from an integral at the cost of reducing the exponents on the other terms. In our case, each time we apply it, we remove one tilde and the main exponent goes down by 1.
So we have $1 of these tail dollar terms, so we can just apply the string equation $1 times.
Exactly. Each application reduces the big exponent by 1. So we start with tail G3 plus 7, and after known of 5 steps, we're left with just tail G2 rangs the count.
A much simpler integral with only one marked point. The paper does add a caveat for the genus 0 case, though.
Yes. For G to R dollars, you have to be careful not to reduce so far that you fall into the unstable range where another is too small. The geometry dictates the limits of the combinatorial tool.
And this final value, G2 Wrangly, is a famous classical result.
It is. The value is known to be 124 GDR, which is exactly the formula for the minimum stated in Theorem 1.2.
Section 2 is complete, providing the full AI-generated proof flow and calculation. Now we move to the modular formalized approach.
Confirmed. The modular approach in Section 3 will formalize the combinatorial steps we just saw.
Section 3 is titled Formalized Proof via an Abstract Optimization Theorem, and it's marked as AI text. The idea here is to separate the abstract optimization logic from the geometric input.
Right. It lifts the problem out of geometry and into pure combinatorics. It considers any function dollars that maps vectors of non-negative integers summing to the dollars to the rational numbers.
And then comes Theorem 3.1, the optimization theorem, which is explicitly marked as lean verified.
Yes, and this is a huge deal. The theorem states that if you have a function dealer dollars that satisfies three simple abstract properties, S for symmetry, LC for log concavity, and P for strict positivity, then it is a mathematical certainty that
A achieves its maximum on a balanced vector, and B dollars achieves its minimum on a concentrated vector.
Okay, this is the perfect time for our final mandatory digression, formal verification and lean. Why is it so important that this theorem is lean verified?
Lean is what's called a proof assistant, or an interactive theorem prover. When a theorem is formalized in lean, it means a computer has checked every single logical step, from the initial axioms all the way to the final conclusion.
So there are no gaps, we can easily shown that, no hand waving, every deduction is mechanically verified.
Exactly. And the fact that the AI models generated this formalization means that the combinatorial engine of this entire paper is guaranteed with machine-level certainty to be correct. The argument that S, LC, and P imply the extremal results is ironclad.
We've established the abstract optimization theorem and its formal verification status. Now for proposition 3.2, the geometric bridge.
The logical dependency is set. Proposition 3.2 must prove the geometric integrals satisfy the necessary axioms.
And that's exactly what it does. Proposition 3.2, which is entirely human-written, is the proof that our descendant function actually satisfies the three abstract conditions: symmetry, log concavity, and positivity.
The proof of S-symmetry is pretty straightforward. It just relies on the fact that you can permute the marked points on the geometric space without changing the value of the integral.
The proof of p-positivity is also cited as well-known, following from the recursive formulas of the Witten-Kontsevich theorem. These numbers are known to be strictly positive.
The real meat of the human contribution here is the proof of LC log concavity.
Right. This is where the human geometer has to do the heavy lifting. The proof starts with the generalized geometric inequality we mentioned earlier from Khovansky and Teissier.
The one that says alpha-1 cactus, alpha-21 beta, alpha-22 beta.
Yes. And the human author has to perform the technical steps to show this applies. This involves dealing with the fact that Melagame is a stack by using that finite flat cover trick. He proves that because the Teissier classes are Neff, the inequality holds, which translates directly into the discrete log concavity for our function dLday.
So the human does the hard geometric work to prove that the real-world object satisfies the abstract rules that the machine has verified.
It's the perfect handshake. The paper then concludes with Remark 3.3, an AI-written summary. Theorem 1.2 now follows immediately from Theorem 3.1 and Proposition 3.2.
The geometric bridge is complete. The abstract axioms are satisfied by the physical descendant integrals. We must now rapidly detail the lean-proof structure for Theorem 3.1.
Confirmed. Sections 3.1 through 3.4 provide the final combinatorial validation.
Right. These sections are the detailed, AI-generated, lean-verified proof of the abstract optimization theorem. Section 3.1 just defines the slice sequence secant again and confirms it inherits palindromicity and log concavity from the main function dollars.
Section 3.2 contains the core combinatorial result, lemma 3.7, the unimodality lemma. This is the formal verified proof that any positive palindromic log concave sequence must be unimodal.
And this proof is purely abstract. It doesn't know anything about geometry. It's just a property of sequences of numbers.
Yeah, exactly. Then section 3.3 gives lemma 3.8. The balancing increases D lemma. This uses the unimodality to prove that if you have an unbalanced vector, moving a unit from the larger exponent to the smaller one increases the value.
And iteratively applying this lemma proves part A of the theorem about the maximum.
And finally, section 3.4 does the reverse. Lemma 3.9, concentrating decreases D, proves that moving a unit from a smaller exponent to a larger one decreases the value.
Iteratively applying that proves part B about the minimum.
The analysis of the lean-verified combinatorial core is complete. We've shown that the abstract axioms mathematically necessitate the extremal results.
Confirmed. We now address the meta-context in the appendices.
Okay, Appendix A is titled Methodology, AI-Assisted Discovery and Proof. This is the behind-the-scenes story.
Section 8.1 confirms the discovery process. Evolutionary search with OpenEvolve, guided by Claude Code, which correctly analyzed the genus Sero case and extrapolated the pattern.
802 describes the submission to improof bench. And this part is fascinating because it highlights the variability of current AI. It says some models gave inconclusive results or even false counterexamples.
And then there's this incredible detail. It says one model hallucinated an entire reference paper. It cited a paper, Zhu, 2018, a proof of the concavity conjecture, a paper that simply does not exist.
This is such a critical data point. The The AI can be brilliant enough to generate a novel proof, and in the next breath, it can be a complete fabulist, inventing sources out of thin air. It shows why human oversight is so crucial.
But eventually, the successful models, multiple GPT-5 evaluations, all converged on the correct log concavity proof strategy.
And that convergence is what gives you confidence that the result is real.
Now, 8.3, partial formalization and lean blueprint, is just astonishing. The author, a professional mathematician, admits he had no prior experience with the lean proof assistant.
So what did he do? He outsourced the entire formalization of theorem 3.1 to Claude Code and ChatGPT 5.2. He acted as a project manager, giving the AI high-level goals, and the AI wrote the code.
He explicitly states, "I did not edit a single line of .lean code." The entire formally verified combinatorial core of his paper was generated by a machine based on its prompts.
That is a paradigm shift. It's AI-enabled skill transfer. You no longer need to be an expert in formal methods to produce a formally verified proof.
And 8.4 notes that AI assisted in the final paper preparation, including finding that genuses or error in its own output and helping with proofreading. They even document the monthly cost of the subscriptions they used.
The transparency is just. It's total. We have fully detailed the life cycle of this paper, from AI discovery to AI-generated formal proof, error correction, and final writing. We proceed to attribution.
Confirmed. Appendix B proposes standards for this new type of collaboration.
Yes. To wrap up the document, Appendix B proposes some best practices for attribution of AI use. This is the author trying to set a standard for the future.
The first proposal is to always include a clear methodology section, just like Appendix A, referencing prompts and code for reproducibility.
The second is a proposal for visual transparency, using the blue-brown markers we've seen to show the provenance of every paragraph.
And the third proposal is about contextualization. The author argues that because of the public hype around AI, authors have a responsibility to explicitly and honestly state the significance of their result, to avoid overstating its importance.
It's an ethical guideline, basically, a firewall against AI-fueled exaggeration. We have finished the appendices and the entire document, including all references and contact information.
Mission complete.
So if we synthesize everything, the historical significance of this paper really lies in its transparency. It documents a completely new scientific workflow.
Right. The AI discovers the problem, multiple AIs independently find the elegant proof, and then another AI formalizes the combinatorial core of that proof with machine-level certainty.
It recasts the role of the human mathematician. They become the curator of ideas, the geometer who builds the bridge between the abstract and the concrete, and the final validator of the machine's output.
And for you, the listener, the core mathematical takeaway is just how often these incredibly complex geometric problems boil down to simple, abstract combinatorial axioms.
Exactly. The reason maximum complexity requires maximum balance in this setting isn't because of some deep hidden formula. It's just because the underlying geometric objects have a basic positivity property, which forces the values into a unimodal bell-like shape. The answer is in the shape, not the numbers.
So to leave you with a final provocative thought, we saw that the human was still essential for Proposition 3.2, the geometric bridge. That required dealing with the technicalities of stacks and applying classical Hodge theory.
But if the combinatorial engine of a theorem can be entirely machine-generated and machine-verified, how long until the AIs can handle that geometric translation step as well? What happens when the AI can write and verify both Theorem 3.1 and Proposition 3.2?
What then is the necessary role of the human mathematician in the process of discovery and proof?
That is the question that will define the next decade of this field.
If you want to explore this further, the author provides his email right at the end of the paper, johannes.schmidt@math.ethers.x. We'll see you next time on The Deep Dive.